So in today's class, we are discussing electromagnetism. When I bring a permanent magnet near a compass, you can see that this end of the magnet attracts this part of the compass needle. And when I turn the magnet around, it attracts the other side of the compass needle. What property of magnetism does it show?
Electromagnets.
No, it shows that like poles repel each other, right? So the north pole here of this magnet is attracting the south pole of the compass needle. If I turn it around, this also turns because the south pole of here attracts the north pole of the compass needle. Right? The north pole here attracts the south pole here. The north pole here attracts the south pole here. Like poles repel each other, unlike poles attract each other. Right? So we have seen that that happens when I bring two magnets near each other, or when the magnet goes to close to a compass needle. But when I bring this is a copper wire. You see in my hand, it is a copper wire. And copper wires you can see in your houses because all the electrical wires have copper wires. If I bring a copper wire near a magnet, what do you think will happen? Attraction? Why? Copper is a metal. If I bring it close to it, will there be attraction? No attraction. There is no force of attraction between the magnet and the copper wire. Why? Because copper is not a magnetic material. Okay? Copper is not a magnetic material. So even if I bring the magnet close to the copper wire, there is no force of attraction or repulsion. In fact, I have one more copper wire here. This looks like a coil, right? It looks like a copper coil. If I bring a magnet close to the copper coil, will there be attraction? No, because this is a copper wire. This is a copper coil. Are they magnetic? They are not magnetic. So if I bring a magnet near a copper wire, there is no force of attraction. Correct? So we have seen that a copper wire, this is a copper wire, is not attracted by a magnet. Correct? Okay. And that is what we saw here. We saw that a copper wire that is brought close to a magnet does not experience any force of attraction because a copper wire is not a magnetic material. But what happens when we pass an electric current through the copper wire? Let us see what happens. If we pass an electric current through the copper wire, you see, this is a copper wire, this is a magnet. Was there any force of attraction between the magnet and the wire? No, right? Is there any force of attraction? No. But I want to pass an electric current through the copper wire. How do you pass an electric current through the copper wire? By using batteries. So I have 4 batteries here. I will pass an electric current through this copper wire using these 4 batteries. So now see what happens. Can you see what happened? There is a force of attraction, right? Can you see that the magnet has been lifted by the copper wire, right? What happens? What happens if I stop the current? If I stop the current, what happened? It fell down, right? So this wire became a temporary magnet. Why? Because when current is flowing through the wire, it became a magnet. Do you agree? See, even now, see, when I lift it like that, is there any attraction? No. What should I do to make it a magnet? I have to pass an electric current and it is lifted. So why does the copper coil do that? The copper coil has an electric current flowing through it, and so it has become a temporary electromagnet. What kind of a magnet?
Electromagnet.
It is a temporary electromagnet. Why is it called temporary? Because now the magnetism is switched on. I can switch off the magnetism by switching off the current. Correct? Now it is not a magnet. If I pass current through it, again it becomes a magnet. If I stop the current, again it is not a magnet. So this is a temporary magnet because I can switch off and switch on the magnetism. Why is it called electromagnet? Because it is a magnet only when what passes through it? An electric current passes through it, right? So we created a temporary electromagnet in this coil by passing an electric current through it using these batteries. So you saw how we can create a very simple electromagnet in this activity. In fact, one more thing we can do is what happened when I brought the compass close to the magnet? You could see, right? The compass is getting attracted to the magnet. What will happen if I bring the copper wire to the magnet? Will anything happen? No, because the copper wire is not magnetic. See, nothing happens here. If I bring it like this, nothing happens. Is the compass needle moving? No. How can I make this into a magnet? By passing an electric current. So let us see what happens to the compass needle when I pass an electric current through the wire. So now can you see what happens? So once again it proves that when current is flowing through the wire, this wire became what? An electromagnet, a temporary electromagnet. Right. So this is a wonderful illustration of how to create a temporary electromagnet. You take a copper wire and when you pass an electric current through the wire, it becomes an electromagnet. So what we did was, by passing an electric current, when an electric current is passed through the wire has a magnetic field around it. It becomes a temporary electromagnet. And those were some of the activities we saw just now. You have studied about the lines of force of a magnet. You remember the diagram in your textbook where you have drawn the lines of force of a permanent magnet, of a bar magnet? Do you remember?
Yes, sir.
So if we want to draw the lines of force of an electromagnet, what will it look like? You must have read about the right hand thumb rule, right? Are you familiar with the right hand thumb rule? No? Let us discuss that. You look at this diagram. In this diagram, this man is using one hand to hold the wire. Which hand is he using? Right hand or left hand?
Right hand.
He is using the wire. He is using his right hand to hold the wire. In this picture, he is using his right hand to hold the wire. And the thumb, his thumb, which is the thumb? This is the thumb. He is pointing the thumb in the direction of the current. So if you hold the wire with your right hand, and if your thumb is pointing in the direction of the current, then the remaining fingers, these fingers, will give you the direction of the lines of magnetic field. Correct. So that is what this diagram means. to show the same thing to you, if you have a straight wire, right, and if current is flowing in this direction, current is flowing in this direction, I have to hold it with which hand? Right hand. And my thumb has to point in the direction of the current. Yeah, I have to point it in the direction of the current. Then these fingers here will give you the direction of the magnetic field, right? So that is what it means. So as you can see in this diagram, the magnetic lines of force are concentric circles. What is the meaning of concentric circles? What are concentric circles? Concentric circles are circles which have the same center. Remember, every circle has a center, right? Circle of the center of the circle. If you have multiple circles like this, and all the circles have the same center, right? This circle has this center. This circle also has the same center. This circle also has the same center. Yeah. Such circles are called concentric circles. Okay? And the lines of force look like this. If the wire, if I'm holding the wire in my hand and the wire is coming like this, I'm holding it with my right hand, then the lines of force will be in this direction. So that is what that picture in the slide tells you. You understand? So when you hold the conductor with your right hand, with the thumb pointing in the direction of the conductor, or in the direction of the current, then the remaining four fingers tell you the direction of the magnetic field. Yeah. Now this diagram tells you the lines of the magnetic field when you have a straight wire. This is a straight wire. What about a wire which looks like a coil? You see this picture here on the right side? That is not a straight wire, right? What is that wire called? That is called a solenoid. Solenoid, right? So what will the lines of force in a solenoid be like? Let us take a look at my drawing on the board and then discuss that. So when you have a solenoid, this is a solenoid or a wire, copper coil. Can you see that?
Yes,
We are now passing a current like that. The current flows through the wire and comes out in this direction. Remember, in your earlier chapter, you would have read about the lines of force around a bar magnet. What does it look like? If this is the bar magnet, then the lines of force go from the North Pole to the South Pole, like that. Right? This is what it looks like, from the North Pole to the South Pole. And they will never intersect each other. They will never cross each other. Similarly here, one end of the solenoid becomes the North Pole, one end becomes the South Pole. Let us say this becomes North, this becomes South. The magnetic field of the solenoid looks very similar to the magnetic field of the bar magnet. And yeah, and the again from the North Pole to the South Pole. Okay, and this is what the magnetic field of a solenoid will look like. Inside the solenoid, the lines of force will go from the south pole to the north pole. Inside the solenoid, it is from the south pole to the north pole, and outside the solenoid, from the north pole to the south pole. And it looks very similar to the magnetic field of a bar magnet. Okay? Now, what happens when a current carrying conductor is inside a magnetic field? So this is the next topic of discussion. What happens when a current carrying conductor is inside a magnetic field? So to understand what this statement means, let us do one small experiment. Now we have a copper wire. You have seen this before. Is it a magnet? If I want to turn it into a magnet, what should I do? I have to pass an electric current. So if I take a magnet like this and keep it here, does it experience any force? No. There is no force between the magnet and the wire because this is not a magnet at all. But what happens when I pass an electric current? It becomes a magnet, right? So now it becomes a magnet. So now this is a magnet and this is also a magnet. Both of them are now magnets. So this is exerting a force on this, and this is exerting an equal force on the copper wire. You understand? So when a wire has a current flowing through it, it becomes a magnet. And when I keep another magnet near it, this has become a magnet. This is already a magnet. So this exerts a force on this, and this exerts a force on this. Right? They are exerting a force on each other. And that is the meaning of force exerted by a magnetic field on a current carrying conductor. This is the current carrying conductor, and this is the permanent magnet. So when the current carrying conductor comes close to a permanent magnet, remember this is a magnet, this is also a magnet. So they will exert a force on each other. And that is the meaning of the statement, force exerted by a magnetic field on a current carrying conductor. That is the meaning. Understood? There is no force if there is no current. Only when current is flowing through the conductor, there is a force. Understand? So in this diagram, you can see that we are talking about the force experienced by a current carrying conductor when it is kept in a magnetic field. Now, you look at this diagram, what is that? The part that I circled, that is the current carrying conductor. Okay, that is a current carrying conductor. Look at this, what is this?
Battery.
So those are batteries. By using those batteries, we are passing an electric current through the current carrying conductor. So when current is flowing through the conductor, what happens in the conductor? It has a magnetic field around it because it has become a temporary electromagnet. Correct? So when current is flowing through the conductor, it has become a temporary electromagnet. So this is a magnet, but we have another magnet in this picture. Which one is that? This is also a magnet. So here we have two magnets. One is an electromagnet and one is a permanent magnet. One magnet is pushing the other. Do you agree? Because both of them are magnets, the magnets exert a force on each other. So the magnet begins to push on the electromagnet, and the electromagnet exerts an equal force on the magnet. And that is what happens. Now, if you want to find out the direction of the force exerted by the magnet on the electromagnet, what will we do? We will use the left hand rule, Fleming's left hand rule. We will hold up three fingers like this from our left hand. This is the index finger, this is the index finger. This is the middle finger. And this is the thumb. When you hold it up like that, the index finger, the pointing finger, should be in the direction of the magnetic field. The middle finger should be in the direction of the current flowing inside the conductor. Remember, there is a conductor and a current is flowing inside the conductor. So this is the direction of the current inside the conductor. What does this indicate? The thumb. The thumb indicates the direction of the force experienced by the conductor. Remember, the conductor has become a magnet, and there is also another magnet there. So the conductor experiences a force because it is sitting inside a magnetic field. The direction of the force is given by the thumb. So this is called Fleming's left hand rule. Okay? Now let us talk about motors. Now, a motor is also operating because it has two magnets. What does a motor do? A motor is a machine which converts what form of energy into what form of energy? Correct. A motor converts electrical energy into mechanical energy. Right. So let us study the parts of the motor, and then we will build a motor here in the lab. We have two or three important parts in the motor. The first part is the permanent magnet. You see the north and south poles indicated here are the poles of a permanent magnet. Right. So the north and south poles are the permanent magnet. You can see that in the picture.
Yes.
Along with the permanent magnet, we need another magnet, a temporary electromagnet. And to create a temporary electromagnet, what do we need? A copper wire. Right? And that copper wire is here. This one, can you see that? The yellow wire in the picture is the copper wire. This one. That is the copper wire. So, is the copper wire magnetic? No. No. It becomes a magnet only when there is a current flowing through it. So that is why we have a battery. You see the battery?
Yes, sir.
So we have a battery, and then we have a current carrying conductor. So when current flows through the current carrying conductor, the conductor also becomes a magnet, a temporary electromagnet. So now we have two magnets here, the permanent magnet and the temporary electromagnet. So the interaction between them, the force exerted by the permanent magnet on the temporary electromagnet causes the coil to rotate. Right? And that is what we call a motor. So if you look at what happens, if you apply Fleming's left-hand rule in this diagram, remember we have three fingers. The index finger should point to what? The index finger should point in the direction of the magnetic field, remember. And what is the direction of the magnetic field in our picture? the direction of the magnetic field is going from the north pole to the south pole, like this. You see the arrow here? That arrow indicates the direction of the magnetic field, because this is north and this is south. And the magnetic field will go from north to south. So the index finger, the pointing finger, should be going from north to south. The second question is, the middle finger should point in the direction of the current. Right? So in the wire, current is flowing like this. It goes, see, it goes from the positive, it goes like this, like this, like this. See that? So now you know the direction of the current also. So you can use the left hand rule and find out that on this part of the wire, the direction of the force is upward. And on this part of the wire, the direction of the force is downward. So when you have this situation where one part of the wire experiences an upward force, one part of the wire experiences a downward force, the wire starts rotating. And that is how a motor works. So to summarize, a motor converts electrical energy into mechanical rotational energy. Rotation is possible because there is interaction between two magnets. One is a permanent magnet in the picture and the other is an electromagnet. And when these two interact with each other, the coil rotates. And the direction of the rotation is given by Fleming's left hand rule. So before we continue for some practice questions, let us try to build one simple motor here. I had shown it to some of you last week, but I'll show it to you again so you can take a look at it. Remember, to build an electromagnet, you need only three parts. We need a battery, because battery supplies electrical energy, correct? You need a permanent magnet. And what is the third thing you need? We need an electromagnet. We need a permanent magnet, we need an electromagnet, and we need a battery to supply electrical energy. So let us build a motor with just three things. So I have a battery here. I have the permanent magnet here. What is missing? What do I need? I need a copper wire, right? I need a copper wire which becomes a temporary magnet. So I will connect it like this. And I will keep the copper wire here. What is it doing? And why does it rotate? Because remember, a motor works because there are two magnets in the motor, a temporary electromagnet, this one, and a permanent magnet. So when there is a force exerted by this magnet on this magnet, it starts rotating. So this is a very simple example of a motor, right? Last week I had shown you one more example. You remember? Let me try to show it to you again. You remember this example? Shall we try to do it once more? See that how it is moving? This also is a motor. And this again has a battery, a permanent magnet, two permanent magnets. And this is not a piece of paper, this is aluminum. It's an aluminum sheet. It acts as the electromagnet. If I keep it on the table, it doesn't move. Why? Because table is not conducting electricity. But if I keep it on the aluminum sheet, it conducts electricity. So that is why it starts moving. Okay? So this is also an example of a simple motor. Okay? We have just a few more minutes left. So let us try to do some practice questions right now. Now here is a question. It's a multiple choice question. Which of the following correctly describes the magnetic field near a long straight wire? Can any of you answer? If it is a long straight wire, then the magnetic field consists of concentric circles centered around the wire. Remember the diagram I showed you?
Yes, sir.
So the option here is, the correct option is D. So the correct option is D. Remember the right hand thumb rule, right? If I hold the conductor with my right hand, so that the thumb points in the direction of what? The direction of the current. Then these fingers give me the direction of the magnetic field, and they are concentric. They are concentric circles around the conductor. The second question, choose the correct option. The magnetic field inside a long straight solenoid carrying current is the same at all points. Very good. So that is the option. It is not zero. It is not decreasing towards the end. It is not increasing towards the end. So the last answer is the correct one. Very good. Why don't two lines of force, magnetic lines of force, intersect each other? So the answer is, if two lines were to intersect each other, that would mean that a compass needle placed at that point would point in two different directions, and that is not possible. At any point in the magnetic field, the compass needle will point to only one direction. It cannot point in two different directions. That means that the lines of force in a magnetic field cannot intersect. Understand?
Sir.
The fourth question is, how does a solenoid behave like a magnet? Can you determine the north and south poles of a solenoid with the help of a bar magnet?
Yes, sir.
How do I do that? Yeah, so I heard the right answer, but let's just do it on the board. I have a solenoid here and a current is flowing through it. We have one pole is the north pole, one pole is the south pole, and I don't know which pole is north, which pole is south, and I have to find out. Suppose I bring a bar magnet near the solenoid. This is the north pole of the bar magnet. If there is attraction between them, that means that this is the This is the south pole, right? If there is repulsion between them, then what does it mean? This is the north pole. That is how we can find out the poles of a solenoid by using a bar magnet. Yes. So that is the answer. Let's go to the last question of today's practice. If AB is a conductor, it is carrying current. So the current is flowing from A to B in the direction, right? It is flowing from A to B in that direction. Okay? There are 2 points. One is the point P and one is the point Q. Okay? The question is, what is the direction of the magnetic field at P and what is the direction of the magnetic field at Q? How will you do it? We use the right hand thumb rule. Imagine that you're holding the wire AB and your thumb is pointing from A to B. It has to be pointing towards B because the current is flowing from A to B. If you hold it like that, if you imagine that you're holding the conductor, what will be the magnetic field at P? What will the magnetic field be at P? To understand this, maybe I'll show it to you on the board. This is our conductor, right? Current is flowing from A to B. I'm holding it with my right hand. So this is the point P. This is A, this is B. Current is flowing like that. This is P and this is Q. Right? When I'm holding it like this, my fingers are pointing inside the board at P and outside from the board at Q, right? Look at this. Look at the direction of my fingers. Inside the board here and outside the board. So the answer to that question is, at the point P, the lines of force are going into the paper or into the board. And at Q, they are coming out of the paper or out of the board. That is the answer to the last question. So using the right hand thumb rule, you can find out the direction of the field at P and Q. The field is stronger when the point is closer. So if P is closer to the wire than Q, then the field is stronger at P. Because P is closer to the wire, the field is stronger. Q is further away from the wire, so the field is weaker. And that is the answer to this question. So today we have discussed multiple things. We have discussed the fact that a current carrying conductor becomes an electromagnet. It acts like a magnet when current is flowing through it. When an electromagnet comes inside a magnetic field, then the conductor experiences a force. That force, the direction of the force can be determined using Fleming's left hand rule. We saw how a motor works. A motor converts electrical energy into mechanical energy. And the direction of the rotation of the motor can be determined using Fleming's left hand rule once again. So all of these we discussed in today's class. So in next class we will talk about other things. Until then, see you. Bye. Any questions before we disband? Do you have any questions? Okay. All right. So thank you for attending the class. I will see you in my next class. Bye.
Thank you, sir.